All right, this is the last lecture on Chapter 3. In the previous lecture, I stated a classification theorem for perfect codes. It stated that the only perfect codes are essentially the trivial codes, the binary replication codes of odd lengths, the Hamming codes, the binary Golay code, and the ternary Golay code. In today's lecture, I'll introduce the important concepts of cosets of a code and syndromes of vectors. I'll prove a one-to-one correspondence between cosets and syndromes. This will lead to a general-purpose decoding algorithm called syndrome decoding, which works for all linear codes of any distance. However, the algorithm will be inefficient in general because of its very large storage requirements. Nonetheless, the notions of syndromes and cosets will be useful in future lectures when we develop more practical decoding algorithms. The syndrome decoding algorithm will need the notion of cosets of a code. And for that, I'll need the following definition. Let C be an NK linear code over the field F, which is GFQ, with parity check matrix H. Let X and Y be vectors of length n over F. We write that X is congruent to Y modulo C if X minus Y belongs to the code. Here are some facts about the congruence relation mod C that you can verify for yourself. First, the relation is an equivalence relation, so it's reflexive, symmetric, and transitive. Secondly, since a relation is an equivalence relation, the set of equivalence classes partitions the set of all vectors of length n over GFQ. I'll call the equivalence classes cosets of C. The equivalence class containing a vector x is C plus x, which is defined to be the vectors y that are congruent to x modulo C. You can verify that a second description of this coset is as the set of all vectors C plus x, as C ranges over the set of all code words. I'll call x a representative of the coset C plus x. Here is a pictorial depiction of the partition of the vector space into cosets. Note that C is itself a coset because C equals C plus 0. Here's an example of cosets. We'll consider the 5-2 binary code C with generator matrix G given by this 2x5 matrix over Z2. Let's find all cosets of C. As I just noted, C is itself a coset, the coset represented by the 0 vector. This coset is comprised of the 4 code words in C, which you can obtain by taking all linear combinations over Z2 of the rows of G. Let's note that C plus a second code word is also equal to the coset C. And you can check this by adding the second code word to the 4 code words in C. Similarly, the coset containing the third code word and the coset containing the 4th code word are both equal to C itself. So the coset C has 4 representatives, namely each of the 4 code words. To find the other cosets of C, we need to consider vectors not already written down. I'll consider these vectors in order of increasing weight. The coset containing the first unit vector can be seen to be this set. I get this set by adding the first unit vector to all the 4 code words. You can check that this coset can also be represented by the other 3 vectors in that coset. So again, this coset has 4 representatives, namely the 4 vectors in that coset. Next, the other 4 unit vectors give rise to these 4 cosets of C. Now I'll look for vectors of weight 2 not already written down. I first consider C plus 1, 0, 1, 0, 0 to get a 7th coset. And then I consider C plus 1, 0, 0, 1, 0 to get an 8th coset. These 8 cosets of C each have size 4, and they partition the set of all 32 vectors of length 5 over Z2. The observations we made in the previous example can be generalized. I'll let you verify the following facts as an exercise. First, as I noted earlier, the coset containing 0 is just the code C itself. Secondly, if y belongs to the coset represented by x, then the coset C plus y equals C plus x. In other words, a coset can be represented by any vector in that coset. Thirdly, all cosets of C have the same size, and that's the size of the code q to the k. It follows that the number of distinct cosets of C is equal to the total number of n tuples over GFQ, which is q to the n, divided by the size of each coset, which is q to the k. And so this number equals q to the n minus k. Next, I'll give you the main definition of this lecture. Let H be a PCM for an NK linear code C over F. The syndrome of a vector x with respect to the chosen PCM is S, which is defined to be H times X transpose. Since the matrix H has dimensions n minus k by n, S is a vector of length n minus k. Since code words are characterized as being the vectors in the null space of H, all code words have syndrome 0. We used the notion of syndrome in the previous lecture in our decoding algorithm for single error correcting codes. Recall there that we received a vector R and we computed H times R transpose. This is the syndrome of the vector R with respect to the PCM H. The next theorem will form the basis for our syndrome decoding algorithm. Let x and y be vectors of length n. Then x is congruent to y modulo c if and only if x and y have the same syndrome. So H times X transpose equals H times Y transpose. And so cosets are characterized by their syndromes. All vectors in the same coset have the same syndrome, and vectors in different cosets of C have different syndromes. The proof of this theorem is short. We have that X is congruent to Y modulo C if and only if X minus Y belongs to the code. This is by definition of the congruence relation. We know that code words are characterized by being in the null space of a PCM for the code. And so X minus Y belonging to C is equivalent to H times X minus Y transpose equals 0. And that's equivalent to H times X transpose equals H times Y transpose. Here's our strategy for syndrome decoding. Recall that if a code word C is transmitted and R is a received vector, then the unknown error vector is denoted by E and is defined to be R minus C. Since R minus E equals C, which is a code word, we have that R is congruent to E modulo C. Thus, the received vector R and the unknown error vector E are in the same coset of C and therefore have the same syndrome. So when we receive a vector R, we look for a vector E in the same coset as R that has the smallest weight. This makes sense because errors of smaller weight are more likely to occur than errors of larger weight. So, the decoding strategy is the following. Given the received vector r, we'll find a vector E of smallest weight that has the same syndrome as r. So H times E transpose equals H times R transpose. With the CMLD decoding strategy, we then decode R to R minus E. With the IMLD strategy, if E is unique, so if there is a unique vector of smallest weight that has the same syndrome as R, then we decode R to R minus E. Otherwise, we reject R and declare that error correction is not possible. To complete the description of the syndrome decoding algorithm, we need to answer the following question. Given a PCM for a linear code and a received vector R, how can we efficiently find a vector E of smallest weight with the same syndrome as R? I'll call this the syndrome decoding problem. The bad news is that no efficient algorithm for the syndrome decoding problem is known. In fact, there is very strong evidence that no such efficient algorithm even exists. The evidence is the fact that this problem is known to be NP hard. The notion of NP hardness is covered in a first course in algorithms. You might not have taken such a course, so let me give you an informal outline of what it means to be NP hard. Now, there is a very large class of yes-no computational problems called NP. This class includes thousands of natural problems from all areas of computer science, graph theory, and other areas of mathematics. The problems in NP have the property that there is an algorithm which, when given an appropriate certificate, can efficiently verify that a problem instance has a yes answer. An example of such an NP problem is the following. Given a number n, is it composite? Another example is, given a graph, does it have a 3 coloring? Within the class of NP problems is a subclass of problems called P standing for polynomial time. These are problems for which efficient algorithms are known, where efficient means solvable in polynomial time. Now, there is a subset of NP called NP hard problems which have the following remarkable property. If any one of the NP hard problems can be solved efficiently in polynomial time, then all problems in NP can also be solved in polynomial time, which would mean that P equals NP. The class NP contains thousands of natural problems that no one knows how to solve efficiently, even though these problems have been studied for decades. And so, if one found an efficient algorithm for solving the syndrome decoding problem, which is known to be NP hard, then one would immediately get efficient algorithms for all problems in NP, which would mean that P equals NP. This would be a truly astounding result. And hence, the NP hardness of the syndrome decoding problem is very strong evidence that no one will ever discover an efficient algorithm for finding a vector of smallest weight with the same syndrome as a received vector.
As a quick aside, let me mention that the problem of computing the minimum distance of a linear code, given any generator matrix for the code, was shown to be NP hard in 1997.
Even though the decoding strategy discussed previously has no hopes of leading to an efficient algorithm for decoding general linear codes, we'll nonetheless present the syndrome decoding algorithm. The algorithm has a setup. For each coset of C, we select an arbitrary vector of smallest weight in that coset and call it the coset leader of that coset. We then store a table of coset leaders and their syndromes. I'll call this the syndrome table. So an entry in the table is comprised of a coset leader, which has n symbols in it, and a syndrome, which has n minus k symbols. The total number of rows in the table is q to the n minus k, because that's the total number of cosets of C, and also the total number of syndromes of length n minus k. The decoding algorithm itself is quite simple and follows the CMLD decoding strategy. Given a received vector R, we compute its syndrome S and look for S in the syndrome table. I'll let the corresponding coset leader be E. We then decode R to R minus E. By design, this decoding algorithm is guaranteed to make the correct decision whenever the error vector is a coset leader. On the other hand, the algorithm is guaranteed to make an incorrect decision if the error vector is not a coset leader. So the only error vectors that the decoding algorithm properly handles are the coset leaders. The following theorem helps us find coset leaders quickly. Let C be an NK code over the field F with distance d. Let X be a vector of weight at most equal to the error correcting capability of the code C. Then X is guaranteed to be a coset leader. So all vectors of weight up to the error correcting capability of the code must be coset leaders. And hence the syndrome decoding algorithm is guaranteed to make the correct decision if the weight of the error vector is at most d minus 1 over 2. Let's prove the theorem. Suppose that y is a vector in the same coset as x, different from x, and of weight at most equal to the weight of x. In other words, I'm assuming that x is not the unique vector of smallest weight in its coset. Since x and y are in the same coset, x and y are congruent to each other modulo c. And so x minus y is a code word. In fact, a non-zero code word. But now the weight of x minus y can be written as the weight of x plus minus y is at most equal to the weight of x plus the weight of minus y. And the weight of minus y equals the weight of y. Now both y and x have weight at most d minus 1 over 2. And so the weight of x plus y is at most equal to d minus 1. So x minus y is a non-zero code word of weight at most d minus 1. This means that the code C has weight at most d minus 1, and so its distance is at most d minus 1. This contradicts the fact that C has distance d. So we conclude that no such y exists. Hence, x is the unique vector of smallest weight in its coset, and so must be a coset leader. Let's do an example of syndrome decoding. We'll consider the 5-2 binary code C with generator matrix given by this 2x5 matrix. We saw this code in slide 82. The GM is in standard form, so we can write down a PCM for the code C. Note that C has distance 3, as you can verify by examining the columns of H. Here is a syndrome table for C. There are 8 syndromes, one for each binary vector of length 3. Among the coset leaders are the vectors of weight 0 and the 5 vectors of weight 1. These vectors are guaranteed to be coset leaders by the theorem we just proved. And so they all have different syndromes. The last 2 coset leaders of weight 2 were chosen arbitrarily among the set of vectors of weight 2. Here's an example of decoding. Suppose that r equals 11011 is received. We compute its syndrome, which is 010, and locate that syndrome in the syndrome table. The corresponding coset leader is 00010, and so we choose that to be the error vector. And we decode r to r minus e by flipping r in its 4th bit position. You can check that C is indeed a code word by verifying that H times C transpose is the 0 vector. Even though syndrome decoding is a conceptually simple algorithm, it's not efficient in general. This is because the syndrome table is exponentially large, and so would take too much time to compute, let alone store. For an NK binary code, the syndrome table has size the number of cosets, which is 2 to the power n minus k, times the size of each table entry, which is the length of a coset leader, n bits, plus the length of a syndrome, which is n minus k bits. So the total size of a syndrome table for a binary NK code C is 2 to the power n minus k times 2n minus k bits. And this is exponential in n minus k. I'll make the small remark that the syndrome table size can be decreased slightly because the table can be sorted by syndrome, and then the syndromes do not need to be stored. In the previous example, note that the syndromes are all the 8 binary vectors of length 3. So these are the binary representations of the numbers between 0 and 7. If we sorted these syndromes by their corresponding integers, then we would no longer need to store the syndromes. This would decrease the size of the syndrome table to 2 to the n minus k times n bits. This is still exponential, and so the syndrome decoding algorithm is still inefficient in general.
Next, we'll study 2 binary goalie codes. First, the binary goalie code C23, which is a perfect code. And then we'll study its extension, namely C24. I look forward to seeing you in V3f.